This presentation is about the IDTC project entitled Pricing Pension, Life Insurance, and Investment Products. The contents of this presentation include the following. We first go through a brief overview of the benchmark approach, which is a framework under which we consider several applications. These applications include dynamic asset allocation for target date funds, long-term investments with subjective preferences, the impact of management fees under the context of variable annuities with guarantees, the optimal hedging of variable annuities with guarantees, and benchmark risk minimization for life insurance contracts. We then make some conclusional remarks. So first, let us look at the benchmark approach. This is an extension of the risk-neutral pricing theory presented in detail in Platon and Hayes, 2006. So we just go through some of simple example of diffusive market model to illustrate the ideas. So we consider a diffusive market model where we have a collection of primary securities denoted as vector process S of T. So it is a diffusive model with a drift vector AT and volatility or diffusion coefficient matrix BT, and WT is a vector Brownian motion. We have a fixed time horizon capital T. We consider a self-financing portfolio denoted as pi t, where pi t is a vector of fraction of wealth invested in the corresponding primary security. And this price process of the portfolio satisfies the next SDE. And its logarithm, by assuming this price process is non-negative, we consider the logarithm of this price process, and it satisfies the next SDE. This is all straightforward. We next consider a portfolio that maximizes the growth rate of this portfolio price process. That is, we find the particular choice of asset allocation at time t, which maximizes this instantaneous growth rate. This problem is simply solved such that this optimal allocation is given by the next expression, where plus here represents pseudo-inverse of a square matrix. After plugging in this expression, the portfolio price process here we denote as S star T satisfy the next SDE, where theta star T is a vector process denoting the volatility of the individual Brownian motions. So we call this a risk loading factor process, and this process is given by the next expression. So we can reparameterize the SDE satisfied by the price process S star T in terms of its drift coefficient alpha T given by the next expression. And we can redefine a scalar Brownian motion through the next expression so that this portfolio we call the growth optimum portfolio satisfy this simple SDE with alpha t as the parameterization process. So given the growth optimum portfolio, which maximizes instantaneous growth rate, we consider an arbitrary portfolio price process S pi t denominated in the growth optimum portfolio GP S star T. And this we call this price process a benchmark price process. And it turns out that benchmark price process satisfies the next SDE, which is a driftless SDE, which means the benchmark price process is a local martingale. If we further assume that the price process of a portfolio is non-negative, then the benchmark price process, which is a local martingale, is also a super martingale. This implies that if we have two portfolio processes, U and V, such that their terminal wealth, their terminal value, terminal payoff is the same, and we assume that Vt is given by the next expression. Which we call this expression, we call it the real-world pricing formula. If we assume Vt satisfies the real-world pricing formula, then it can be easily shown that the benchmark price process U hat T is greater than or equal to V hat of T, which means Ut is greater than or equal to Vt. This means that given the same terminal value of the price process U and V, V is less than or equal to U for arbitrary U. So that means V is the minimum value of the price process such that the same terminal payoff is realized. So this means that the real world pricing formula, the second formula here, is the minimal possible pricing formula for a given terminal payoff among all portfolios or non-negative portfolios that realize the same terminal payoff. This is the idea behind benchmark approach. So in order to apply this formula, we need to have a model for the gross optimal portfolio, S star T, which satisfies the SDE we have shown before with an unknown drift process alpha T. We specify this alpha T to be given by this simple exponential function. We have some heuristics behind this choice of parameterization, which I will not go through here. So after this parameterization, we have we get this SDE satisfied by the GPS star. And this model, we call it a minimal market model. The minimal market model is solvable, has a closed form solution in the sense that the transition density of this SDE can be obtained in closed form. To see that, we consider this change of variable, change of time, where we redefine the time tau as an integral of this drift coefficient over t. And when denominated in the tau time, the S star process satisfies the next very simple looking SDE, where W tilde star is a Brownian motion under the time tau. And this SDE represents a squared Bessel process. So that is closed form solution, so that closed form transition density is available in terms of Bessel functions. To further simplify the minimal market model, we consider this normalized GP, which is the GP normalized by the drift coefficient in some way, such that this normalized GP satisfies the next SDE, which is a mean reversion process, stationary mean reversion process. And the transition density of this normalized GP is given by that of a chi-square, a non-central chi-square random variable. So that's the closed form solution of the transition density for the normalized GP. So given this closed form transition density, it also makes possible exact simulation of the minimal market model. In particular, all we have to do is simulate this chi-square random variable, which can be done by using the inverse transformation method, such as shown here. So we generate some uniform random variable u and apply the inverse CDF of chi-square distribution, and we get a realization of the chi-square random variable. On the other hand, if we observe a chi-square random variable, we apply the CDF, we get a uniform random variable. So given the minimum market model, we want to estimate its parameters. So we take the S&P 500 as the approximation of the GP of the U.S. domestic equity market. Again, there is some justification behind this approximation, which I will not present here. So here's a plot of the discounted S&P 500 log prices for the last 30 years, for the last 80 years. So the log price shows a clear linear trend. So to estimate the minimum market model, we consider three approaches: maximum likelihood, and a Markov chain Monte Carlo based method, and a quadratic variation based method. So for the maximum likelihood estimation, all we have to do is that we realize that given the empirical data, we can back out the chi-square random variables of the transitions, and we can write down immediately in closed form the likelihood of those chi-square random variables. And by maximizing this log likelihood expression, we can determine the two parameters, eta and alpha 0, that are used to parameterize the minimum market model. The Bayesian Markov chain Monte Carlo estimate is following standard approaches, and the quadratic variation estimator is a little alternative approach. All of them give very similar results, so that we will stick with the maximum likelihood estimate for the examples that we will consider subsequently.